Well, buckle up, because today we're going on a deep dive into the quantum world.
To explore.
Yeah, to explore the bizarre realm of quantum spin. And trust me,
It is bizarre.
and also beautiful.
It's incredible how this tiny property of particles
Yeah,
is behind this everyday force we all experience with magnets.
absolutely.
And so much more.
So much more.
We've got some dense technical excerpts to guide us.
Sounds fun.
But don't worry, we'll break it all down together.
Yeah, quantum spin is often seen as this mysterious thing,
Mm-hmm.
but it's actually incredibly elegant once you start to see the patterns.
Okay, so our source material really emphasizes this point.
Okay.
That quantum spin, while behaving like other properties of particles like mass or charge,
Right.
doesn't actually mean the particles are physically spinning.
Yes.
Like my head is spinning a little bit.
It's understandable.
How can something have spin without actually spinning?
The term spin is a bit misleading.
It conjures up this image of a tiny sphere whirling around.
Right, like a planet.
Yeah, exactly.
Okay.
But it's more helpful to think of spin as a fundamental characteristic, like an intrinsic angular momentum that these particles just have.
It's built in.
Built in, yeah.
Okay, and our source mentions electrons can have a spin of up or down.
Right.
Is that a simplified way to visualize it?
Yeah, it is.
Or is that really what's going on?
It is a simplification,
Okay.
but it's a useful one for now.
Okay.
Think of it like this. Each electron has this intrinsic property we label as spin,
Okay.
and it can be in one of two states, which we arbitrarily call up or down.
Okay, so it's less about the particle doing a pirouette
Yeah,
and more about it having this inherent property.
exactly.
Okay.
And these up and down spins play a critical role in how electrons interact.
So like a matchmaking system
Exactly.
for the atomic world.
Yeah, that's a great way to put it.
Okay, cool.
Because not every electron can pair up with every other electron. They have to be compatible. And that's where the Pauli Exclusion Principle comes in.
Okay, the Pauli Exclusion Principle.
This is huge.
It's a big one.
This is a fundamental rule in quantum mechanics.
Okay.
It states that no two electrons can occupy the same quantum state simultaneously.
So they need their own unique space.
They need their own space, their own quantum asterisk, if you will.
Right.
And that address includes their spin.
So if two electrons want to share the same orbital,
Right.
which is kind of like their energetic home.
Yeah, like their little apartment.
Exactly.
They can't both have the same spin.
They need to have opposite spins.
They need to have opposite spins, exactly.
It's like a cosmic dance.
It is a dance.
To make sure they don't step on each other's toes.
They have to be in sync, but in opposite ways.
Okay, I like that.
And this principle underpins the formation of chemical bonds,
Right.
the very connections that make molecules from individual atoms.
So we're talking about covalent bonds, ionic bonds, metallic bonds.
All of them?
Our source lists all three.
Yep.
But let's focus on covalent bonds for a second.
Okay.
Because they seem like the best example of this quantum dance of spin.
Yeah, absolutely.
You know, in action.
So take the oxygen we breathe, O2.
Okay.
Each oxygen atom needs two more electrons to complete its outer shell.
Oh.
So they team up and form a double covalent bond,
Right.
sharing two pairs of electrons.
Right.
And here's the key. Each shared pair has electrons with opposite spins.
So they can coexist.
It's a delicate balance to ensure that partnership is stable.
So this tiny property of spin is actually what allows us to breathe.
It's one of the many things it's responsible for.
Wow, that's pretty incredible.
Yeah.
But it doesn't stop there.
No, it doesn't.
Our source hints that spin does even more.
Oh, yeah.
It affects a molecule's magnetic personality.
Mm-hmm.
We're talking paramagnetism and diamagnetism.
These are big words.
They are big words.
But they're not that complicated.
Okay, break them down for us.
All right, so imagine you have a bar magnet.
Okay.
Paramagnetic molecules, like our friend oxygen,
Are drawn to this magnet.
Okay.
And that's because they have unpaired electrons.
Mm-hmm.
Think of these unpaired electrons like tiny magnets themselves.
Okay.
They want to align with the external magnetic field,
Right.
and that's what causes the attraction.
Okay, so diamagnetic materials are the opposite.
Yeah, they're the wallflowers of the magnetic world.
Okay, so they repel magnets.
They do. They have all their electrons paired up.
Okay.
So their magnetic fields essentially cancel each other out,
Okay.
leading to a slight repulsion from the external magnet.
Okay.
It's more subtle than paramagnetism, but still influenced by spin.
Okay, now wait. You mentioned oxygen is paramagnetic.
I did.
But doesn't oxygen have an even number of electrons?
It does.
So shouldn't they all be paired up?
You would think so,
Yeah.
but oxygen's molecular structure actually leaves it with two unpaired electrons.
Oh,
giving it that magnetic personality.
interesting.
And we actually use this paramagnetism in medical imaging.
Really?
MRI machines rely on it.
To create detailed images of our bodies.
Wow, I had no idea.
It's pretty cool, right?
It's incredible to think that something as abstract as quantum spin
Yeah.
is behind such a crucial technology.
It's everywhere.
Yeah, it's like we're peeking beneath the surface of everyday things and finding these incredible connections.
And it's all connected.
But our source goes even deeper,
Oh, boy.
talking about exchange interaction,
Yeah.
which it says is a consequence of this need for...
Anti-symmetric wave functions.
Yeah, I'm already lost.
It sounds intimidating,
It does.
but it's actually pretty straightforward.
Okay.
We'll get to it.
Okay, good.
Don't worry. Welcome back to our deep dive into quantum spin.
We're ready to go deeper.
All right, let's do it.
So we've laid the groundwork.
Mm-hmm.
We kind of understand what spin is.
Sorta?
At least we can visualize it a little bit.
Yeah.
But now our source material goes into how it's represented mathematically, which I have to admit is a little daunting.
It can be.
But hopefully we can make it fun.
We'll try our best.
Where do we even begin with describing spin mathematically?
Well, we start with something called wave functions.
Wave functions.
These are mathematical expressions that describe the state of an electron,
Okay.
including its location energy and, importantly, its spin.
So it's not enough to just pinpoint where an electron is. We need to factor in its spin as well.
Absolutely.
Oh, yeah.
Spin adds another layer of information, another dimension to our understanding of these tiny particles.
Got it.
So these wave functions,
Yeah.
they're like a complete profile of an electron.
Okay, cool.
And they're essential for understanding how electrons behave and interact.
Now, our source mentioned something about the anti-symmetry of the wave function.
Right.
What does that even mean?
So this is a fundamental property of electrons.
Okay.
They're classified as fermions.
Fermi.
And if fermions have this quirk,
Okay.
their wave functions have to be antisymmetric.
Antisymmetric.
It means that if you swap the labels of two electrons in the wave function, the mathematical sign of the function flips.
Okay.
Think of it like a mirror image.
Mm-hmm.
The wave function changes its reflection when you swap the particles.
Okay, I think I'm following.
Good.
It's like this anti-symmetry is built into the math
It is.
that describes these particles.
Yeah, and it has some pretty profound consequences.
Like what?
Well, remember the Pauli Exclusion Principle we talked about earlier?
Yeah, no two electrons can occupy the same quantum state.
Exactly.
Right.
And that's a direct result of this anti-symmetry requirement.
Oh, I see.
Two electrons can't occupy the same state.
Yeah.
Because if they did, their wave functions would become symmetric.
And that's not allowed.
That's a big no-no in the quantum world.
Okay, so it's like this cosmic dance
Yeah,
where each electron needs its own unique move.
exactly.
And this anti-symmetry ensures that happens.
It's the choreographer of the quantum world,
I love it.
keeping those electrons in check.
Okay, now our source also says that this anti-symmetry leads to the exchange interaction, which affects how strongly atoms bond.
It does.
Can you unpack that a bit further?
Sure. So imagine two electrons with opposite spins sharing an orbital.
Mm-hmm.
Their wave functions overlap,
Right.
creating a sort of interference pattern.
Yeah.
Now, because of this anti-symmetry requirement,
Yeah.
this overlap actually leads to a lower energy state for the system,
Okay.
making the bond more stable.
So it's like this anti-symmetry creates a bonus attraction
In a way, yeah.
between the electrons, strengthening the bond.
Exactly.
Because they have to stay anti-symmetric.
It's wild, isn't it?
It is.
It's like this hidden force that emerges from the way these wave functions interact.
So is this exchange interaction something we can actually measure?
Oh, yeah.
Or is it purely theoretical?
It has measurable consequences.
Okay.
It affects the bond lengths, the bond strengths, the energy levels of molecules.
So it's not just some abstract mathematical concept.
No, it's very real.
Okay, that's good to know.
It's one of those things that reminds us that the math is describing something real.
Right.
It's not just a bunch of equations.
Okay, so we've gone from visualizing spin up and spin down to understanding how the mathematical description of those spins
Yeah.
directly impacts the strength of chemical bonds.
It's a lot to wrap your head around.
It is.
But it's pretty amazing when you think about it.
Now, I remember we talked about electron correlation,
Right.
which seemed incredibly complex.
It is complex.
How do scientists even begin to calculate
Yeah.
the influence of all these interacting electrons?
Well, it's definitely a challenging problem.
I can imagine.
But we have some powerful computational tools at our disposal.
Okay.
Techniques like configuration interaction and density functional theory
Okay.
allow us to model these intricate interactions and predict the behavior of molecules with remarkable accuracy.
Configuration interaction.
Yeah.
Density functional theory.
It's a mouthful.
They sound like topics for a whole other deep dive.
They could be.
We might have to do that.
Yeah.
But the key takeaway is that these methods help us account for the fact that electrons don't exist in isolation.
Right.
They're constantly pushing and pulling on each other.
It's a very dynamic system.
So we can't just ignore electron correlation.
No, definitely not.
If we want to get a complete picture
Right.
of how atoms bond and molecules behave.
It's a crucial piece of the puzzle.
Now, our source mentioned something called spin multiplicity,
Okay.
which sounds a bit mysterious.
Spin multiplicity.
Yeah, what exactly does that refer to?
So it's a way to describe the total spin state of a molecule.
Okay.
It's related to how many unpaired electrons there are.
Okay.
And it plays a crucial role in determining a molecule's magnetic properties.
So if a molecule has lots of unpaired electrons,
Yeah.
does that mean it has a high spin multiplicity?
Exactly.
Okay.
And a high spin multiplicity often translates to stronger paramagnetic behavior.
Right, because each unpaired electron is like a tiny magnet.
Right. The more you have, the stronger the overall magnetic effect.
This is making me think about the incredible diversity of molecules out there. We have everything from simple diatomic molecules like oxygen
Yeah.
to these complex biomolecules that make up our very being.
And everything in between.
And the principles of quantum spin apply to all of them.
All of them.
It's a universal language
It really,
that governs the behavior of matter at the atomic level.
and beyond.
It's truly remarkable how this one tiny property
Yeah.
can have such profound implications.
It's mind-boggling.
We've gone from talking about individual electron spins to understanding how they contribute to the collective behavior of entire molecules.
It's a beautiful journey.
It
It's
is.
through the quantum world.
Now our source teases us with some even more mind-boggling concepts,
Oh, yeah.
like quantum spin liquids and topological insulators.
We're saving the best for last.
Sounds good.
Get ready to have your mind blown.
All right, we're back for the final part of our quantum spin deep dive.
It's a grand finale.
We've explored the basics. We've gotten a little bit into the math. Now it's time to push the boundaries.
Let's get weird.
Our source mentions these things called quantum spin liquids and topological insulators.
This is where things get really interesting.
I'm ready to have my mind blown.
Buckle up.
So first up, quantum spin liquids.
Okay.
Our source describes them as materials where the electron spins are in a constant state of flux,
Right.
never settling into a fixed pattern.
It's like a dance floor where everyone is moving, but there's no choreography,
So there's no pattern.
no synchronized steps, just pure chaotic motion.
Even at really low temperatures,
Even at absolute zero,
where you'd think they would freeze.
you'd expect them to settle down,
Yeah, into a fixed order.
but they just keep on jiggling.
So it's like a never-ending dance party for the electrons.
That's one way to put it.
But if they're always fluctuating, does that mean these materials don't have any magnetic properties?
That's a good question.
Yeah.
They do have magnetic properties, but they're very unusual.
Okay, so not like a typical magnet.
No, they lack that long-range magnetic order you'd find in a normal magnet.
Okay, but they're still magnetic in some way.
Right. They can host something called fractionalized excitations.
Fractionalized excitations.
Yeah, it's a mouthful.
It is. What does that even mean?
So, in most materials, the spin of an electron is considered a fundamental indivisible property.
Yep.
But in quantum spin liquids, the spin can behave as if it's split into separate particles, carrying fractions of the original spin.
So it's like the electron spin has shattered into pieces,
Sort of.
each with its own independent dance move.
It's like the rules of the quantum world have been bent.
That is truly mind-bending.
It highlights the strangeness and beauty of quantum mechanics.
So what makes these quantum spin liquids so special?
Well, for one, they have the potential to revolutionize fields like quantum computing.
Quantum computing.
Imagine building a computer that leverages these exotic spin states to perform calculations in ways unimaginable with classical computers.
So we're talking about a whole new level of computational power.
Exactly, and it's not just about computation.
What else?
Quantum spin liquids could also lead to breakthroughs in materials science and our understanding of fundamental physics.
Okay, so a lot of potential.
A whole lot of potential.
Now on to topological insulators.
Another bizarre but fascinating material.
Our source says they act as insulators in their bulk.
meaning they don't conduct electricity through their interior,
Okay.
but on their surface, they conduct electricity with remarkable efficiency.
So they're like a Jekyll and Hyde material.
Yeah, insulating on the inside, conducting on the outside.
What's going on there?
It all comes down to something called time reversal symmetry.
Okay.
And its interplay with the electron spins.
Time reversal symmetry.
Yeah, it's a bit of a head scratcher, but essentially this symmetry protects the surface currents from being scattered by impurities or defects, allowing them to flow without resistance.
So it's like they have a highway for electrons on the surface.
Exactly, a superhighway with no traffic jams.
And this makes them good for electronics.
Incredibly promising for electronics and, again, quantum computing.
So from frictionless electronics to quantum computers that harness exotic spin states,
Yeah.
it seems like the future is going to be heavily influenced by this tiny property we call spin.
It's the future of technology.
And we've journeyed from this simple visualization of spin up and spin down to the frontiers of quantum materials.
It's quite a ride.
It has. We've explored the mysteries and potential of quantum spin.
Hopefully we haven't spun you out too much.
We've covered a lot of ground.
We have.
But this is really just the beginning.
There's so much more to discover.
Absolutely. So keep exploring, keep questioning, and keep those spins spinning.
And join us next time for another deep dive into the world of science.